Okay, we're at 11 o'clock Mountain Time, so welcome everyone. This is the ComStock Standard Dataset Release for our commercial 2024 Release 2. My name is Chris Caradonna, and I will be your presenter today. I'm assuming a few people are still trickling in. We're going to get started. The first few slides are fairly logistical. Okay, so we are recording the webinar and everyone is muted, but we do have a Q&A box that you can send us questions. Many of those questions will be answered directly in the Q&A, so please check back there to see if your question had been answered. But we will also try to reserve a few minutes at the end to do some live questions if there are any. And then all of the contents, including the webinar slides and the recording, will be available next week, and you will be notified by email with links to all of this. Many people to thank for this effort. Of course, the ComStock and ResStock teams, Open Studio and Energy Plus teams, Lawrence Berkeley Argonne and Pacific Northwest National Laboratory, and then a special thanks to the U.S. Department of Energy Building Technologies Office. So our agenda for today, I'm going to go over the background of the project, how we approach stock modeling with ComStock, what is ComStock, the new measure scenarios that we're adding to this release, how to access the data set. If you've joined us before, there are a few changes here, so I encourage you to stay for this section, just to understand how the data set has changed and how that might impact your workflow. And then some next steps, our future release schedule, and some new measures, and our live Q&A. Before we get going, though, Alyssa is going to put up some prompts for some questions, and we'll wait about a minute for some polling. Okay, seeing things level off a little bit here, so I'm going to end the poll. Thank you all for participating. Okay, so we're going to start with the project background. The main goal here is to help cities, states, and utilities and other major stakeholders have the information that they need to make informed decisions about their building stock with the intent of offering them the best possible outcome. So helping to answer questions like, which energy efficiency pathway will reduce grid strain in my city or maximize reduction in utility bills? Just some terminology and the roadmap of this continued effort. We finished the 3-year end-use load profiles, or EULP, project in 2021. This was a large-scale calibration effort of our ComStock and ResStock tools. And then we continued on with the end-use saving shapes project, which added the impact of energy efficiency what-if scenarios to these baseline stock models so that we could understand the impact. Since 2022, we've released 2 residential and 3 commercial data sets. We're really just continuing this effort. The project is now called Standard Dataset Release. It's largely the same thing, but the name is meant to represent the full scope of the project effort, which includes more than just measure scenarios or end-use saving shapes. But of course, end-use saving shapes are still included in the data set. Okay, so yeah, the intent here is to put information into the hands of decision makers to help realize DOE's goals of increasing building energy efficiency in a way that is both affordable and resilient. The data sets provide a lot. Just to name a few, we have building stock characterization, That would be like, which buildings are in my stock? How many of them? What are their square footages? What are their HVAC system types? Then how, when, and where buildings use energy, impacts of the measures. And the information is used for a variety of ways too, and to help aid in energy efficiency decision-making, or if you're developing a building performance standard or code, and many more. So some terminology. I like to think of the data sets in two parts, at least in the context of what's on the slide here. We have our ComStock baseline, which describes how and when energy is used in buildings today, or as the orange box tells, the building stock of 2018, and we use 2018 weather. And then we have our ComStock measure scenarios, which describe how and when energy is used in a what-if scenario. So we take the baseline models, we modify them in some way. Let's say we're increasing wall insulation, and we simulate those as well, and then we can understand the difference and the impact of applying that measure scenario. Okay, so a standard data set release, what is included? We have updates to our baseline ComStock model. I'll be going over those in the next slide. We have our existing measure scenarios. So we already have 30 measures published in past releases. Those will be resimulated or have been resimulated with the new ComStock baseline and are included in this data set. And then additionally, we have 9 new measure scenarios that we are adding. The 9 new measure scenarios are what we will be going over today. Previous commercial data sets will remain available. If you're new here and have never used ComStock, we encourage you to always just use the most recent data set. But if you currently have a workflow set up that's using an older data set and you want to continue to do so, just know that that will remain. Okay, so now our approach to stock modeling. This webinar is largely focused on ComStock, but just note that this translates a lot to the ResStock or residential modeling tool as well. But we start with understanding the characteristics of buildings in the building stock. So to model the commercial building stock, we need to know the variety of properties that influence energy behavior of buildings. To name a few, that could be like your building type, like is this an office or a hospital? The size of the building, location, the HVAC system type. And we get this information from a mix of both public and private data sources. We then use that to create probability distributions of these attributes. Those really just inform us of the frequency and probability that a certain characteristic appears in the stock. Taken together, that is used to help us articulate a representative set of 150,000 open studio energy models. So this ensemble of energy models would reflect the variety of properties in the building stock. And then for the measure scenarios, we apply the various what-if scenario changes to the models. That's one of the key benefits of using this bottom-up physics-based modeling is we control all of the inputs. So we can model the baseline, but then we can tweak settings in there or inputs to reflect whatever change we're trying to represent to understand the impact. And then using our high performance computing system, we do our simulations, we process and publish the data, and we apply scaling factors. So ComStock currently models the 14 building types on the left side of the screen. On the right side of the screen are building types that we do not yet currently model, according to the Commercial Building Energy Consumption Survey. Also from CBEX, the estimates of the building types that we do not currently model make up about 36% of the stock energy usage for commercial buildings. So for the intents and purposes of this webinar, when I talk about stock savings, I'm talking about the part of the building stock that ComStock currently models. So baseline updates since last release. We're always doing continuous improvements. The biggest one for this cycle is a new sampling methodology to increase geospatial resolution. This is a fairly large change. I'm going to talk about it more later in the webinar. And then some other changes like updating our tool versions and some general bug fixes. We also have some future improvements for this year. We're adding new building types, including grocery stores and other public building types, improving our zoning methodology and water drop profiles. We're hoping the water drop profiles enable us to do water heating measures. updating to a new CBEX for HVAC distributions. So the HVAC distributions inform at what frequency and where do different HVAC systems appear in the stock. We're going to be using the newer version of CBEX for that. We're currently using 2012. And then electrical panel sizing and some further calibration. To the right is a bar chart showing annual site energy consumption between 2024 release 1, that was our past release, and 2024 release 2, which is our current release. And this is by end use and fuel type. Okay, so our new sampling methodology. The big thing here is that we have increased our geospatial resolution, which allows us to have higher confidence when analyzing small or rural geographies. If you joined us before, we've cautioned against filtering down to smaller rural geographies because you could end up with very few ComStock models representing the region. And that doesn't give us a whole lot of confidence that that couple of models is representative of that region. This could still be a problem in some cases, but it should be far less so. So we still encourage you to use common sense when looking at sample size and make sure there are enough samples with very localized data. But again, this should be a far less of an issue now. Building models are now reused across census tracts when they align with key sampled traits. This basically means that previously, a building ID was used once in ComStock. A model represented only one building. Now we reuse that building multiple times across census tracts when they align with key traits of the census tract. This is really what enables us to have our higher resolution. We're also modeling more diversity of low-frequency building types and fewer high-frequency building types where the additional diversity is not helpful. So for example, hospitals are not a very common building type. There's a few by count of them. So before we were not sampling many of them, and that meant hospitals didn't have a whole lot of variability in our model. But now we're sampling more of these lower frequency types to increase that kind of variability. So overall, better representation of stock variability. You may have noticed that we are running 150,000 models now, and previously we were doing 350,000. So we have reduced the amount of models that we're simulating, but in the end, we still think this is giving us a better representation of variability. Changes to the annual results files. We're now offering results files at various aggregations. This is to help manage file size. With the increased resolution, there's just a lot more data. So we're providing different aggregations so that if you don't need that extra resolution, you don't have to have massive files. I will be talking more about that in the accessing the data section of this presentation later on. And down below is a link to the user resource guide for new sampling. It will go into a little bit more detail explaining this and how to consider it for your workflow. Okay, so this is just a conceptualization of the new sampling. My goal here, I don't need you to understand fully how the sampling works or anything like that, but really just, again, to conceptualize it for how it might impact your workflow. So previously, on the left, we would pick a few models or sample them at random in a region. So down below, we can see we're choosing four buildings to sample. And those are what we would model, and we would scale them to represent the area nationally. Now, on the right, we reuse models when the key attributes coincide with what we're looking for across different census tracts. So now we're modeling everything. So we have a lot more models representing regions and therefore a lot more granularity of data. This is especially helpful if you're trying to investigate a county, especially a rural county or a city or something like that, a smaller geography. Okay, and we have documentation on the ComStock baseline that goes into the methodology and assumptions behind ComStock. That's linked here on the top, as well as an introduction to ComStock slide deck that goes into a little bit more detail than what I was able to go over today, just on how ComStock works and what's included and all that. Down below, you also see an email address, comstock@nrel.gov. Please email us with questions, feedback, suggestions. We're fairly active on this email address. Okay, a few highlights. So segmentation reports, we are currently releasing and should be available in February, a series of reports that provides energy data and building characteristics for local geographies or clusters. We have 80 clusters, and therefore there will be 80 reports for these geographies. And these are really to help policymakers understand their local building stock, the energy use, emissions, and identify opportunities in a report format so that they don't have to access the data set. And those are not currently up, but they will in February be at the link below here on the screen. Another highlight, so building performance standards technical assistance. We are now offering this to help develop these programs. So at the bottom, there's a link to request technical assistance. And basically, we will provide a workbook with the local building stock data for setting performance targets and prioritizing measures and technologies. And the top link is a website just on the building performance standards. Okay, and this isn't so much of a resource as much as a framework, but a research highlight. So we have a new framework for identifying building energy models using smart data. This paper was just published called The Framework for Identifying Building Energy Models of Localized Utility Service Areas Using Smart Meter Data. If you're interested in this kind of framework or methodology, I encourage you to look at this report, and it's linked below. Okay, so now we are going to talk about the new measures. So just please note, we're constantly, continuously updating the ComStock model with new information and methods, and that will continue to occur. And we release data sets to capture these changes in 3-month increments now in 2025. So in 2024, we were doing 6-month increments. Now we're doing 3 months. We will not do a webinar for each. We'll probably only do 1 or 2 webinars a year, but just be on the lookout for more frequent releases from ComStock. Measures are not intended to be comprehensive of a technology. That just means that a given technology can have many assumptions, many ways of running it, many products of the same technology. We're not claiming that our way of modeling a technology is the be-all, end-all. And as additional data becomes available, we can, of course, update these measures. We will also be going over results in the presentation today. These are really just high-level observations to introduce the data. These are by no means comprehensive, but we do have these measure documents that go a little bit more into interpreting the data, if that's of interest to you. They also go more into the methodology, the assumptions, limitations that you should be aware of, and again, observations from the results. So those are linked below, and a screenshot of the website is over there to the right. Also at this link is where you will find all of our past EUSS or SDR webinar slides and recordings, and where this recording and webinar slide deck will be uploaded to next week. Okay, so first I just want to call out, as I mentioned, that we do currently have 30 existing measures in ComStock. A few of them are listed here, like LED lighting, heat pump rooftop units, and so on. These are included in the new data set, but I do not focus on them in this presentation. For a full list, go to the link below. It's the same link that we were looking at on the last page with all of our measure documents. Okay, so these are the new measures for this release. I'm not going to be going through this table. I just wanted to have everything in one spot as a resource for you all if you're looking back at this slide deck, but we'll go through these one by one. We have an ideal thermal air loads measure, a bunch of heat pump RTU measures, some packages, and some demand flexibility measures. Okay, so starting with ideal thermal loads. So this one is actually not a technology. It's for information only for understanding raw heating and cooling loads in ComStock models, which has been a pretty common request over the past few years. So instead of reporting the impacts of some technology, we're just reporting the raw heating and cooling loads. These will be reported as district energy in both the annual and time series data, and they are agnostic of the existing HVAC system type. To do this modeling, we actually remove the existing HVAC type and model everything just at 100% efficiency without fans or pumps. And this is applicable to 100% of the ComStock floor area. So all of the ComStock models will have this as a resource for them. Okay, so for results, and again, this isn't so much results because this isn't a real technology, but I just want to help with the interpretation of what you can find with this in the data set. So again, all heating and cooling usage is going to be reported under district energy, regardless of the starting fuel. And we can see that in the right. The red and the blue are heating and cooling. And on the right side with the ideal thermal loads, the dotted and hatched are the district energy sources. So everything for heating and cooling is converted to district energy. Cooling is much higher. This is because we're reporting the pure load rather than the energy usage. So we no longer get the benefit of that COP of DX cooling systems of 2 to 4 times. So don't be surprised when the cooling load appears much higher than what the baseline was showing for site energy usage. And it's the opposite for heating. Heating is reduced a bit because we're replacing 80% efficient combustion systems with 100% efficient systems. You'll also notice a little thin sliver of pink over there. That is remaining fan energy. I said before that we removed the HVAC fans, but we did leave zone exhaust fans, which we're viewing as more of a process load. So you will still see a little bit of fan energy. Okay, standard performance heat pump rooftop units. So in the past, we have released a series of heat pump rooftop unit measures. We're now calling that advanced performance, and that represented top of the line efficiency, variable speed systems. But we got a lot of requests for offering a more standard performance heat pump rooftop unit that might be a little less expensive for an upfront cost. So that's what we're going over here today. So the concept is the same as the other heat pump RTU measures if you're familiar with them. We replace existing gas and electric RTUs. That's about 34% of the stock floor area in ComStock. And the performance that we're using to model these is averaged across manufacturers' public data for performance maps. So all of the data that we use to generate the performance curves is public, with the exception of a few. If you're interested in that, we talk about it a lot more in the reports. I'm not going to be going over that level of detail today. These use reverse cycle defrost, so we're using the heat pump to do our defrosting. And like our other heat pump RTU measures, we size to cooling with electric supplemental heating to address any unmet load. Standard performance is not necessarily like an official category. Many manufacturers offer units that say standard efficiency or something like that. So I tried to outline what our interpretation of standard performance means. And although there is some variety, we found these to be 2-stage cooling units, single-stage heat pump for heating. The heat pump has a minimum lockout temperature of around 0 degrees. So below this temperature, the heat pump doesn't operate and you only have backup heat. There's a few efficiency metrics here. One thing I like to call out is the capacity and efficiency retention at 0 degrees compared to the heat pump's rated capacity is 40%. So going from 47 to 0, we maintain about 40% of our capacity and efficiency. Okay, so savings. So to the right, we can see a plot that has our ComStock baseline representing the stock of today. In the middle, the advanced performance that we released in past cycles, and now the new standard performance measure. So comparing standard performance to baseline, we see 27% heating natural gas savings. That's really just attributed to removing natural gas systems and turning them into electric heat pump systems. So fuel switching. You might ask why this is not 100%. And the reason is right now we're looking at the total building stock, not just the buildings that were applicable to the measure. And then likewise, we have negative 54% heating electricity savings. So again, we're fuel switching, we're adding electric heat. So we get an increase in electric heating. And then we have some fan and cooling savings. These are really just attributed to the cooling and fan systems in these newer heat pump RTUs, replacing older RTUs in the ComStock baseline that just have lower efficiency and often are constant volume fans and constant speed compressors. And then if we compare the standard versus advanced performance, again, advanced is variable speed, top of the line. The standard performance uses more electric heating, cooling, and fans. That's just due to the efficiency difference of them. Okay, so now we're going to look at utility bills, and we'll see similar plots for other measures too. So just to explain this for a minute, we do not model a single electric utility rate for ComStock models. We model many of them, up to 50, based on what was applicable to the building for its region. So what I'm showing here is kind of the range, right? We have the maximum, the mean, and the minimum. There are more available in the data set, but this should give us an understanding of the range of outcomes that we can expect based on the utility rate. Natural gas, fuel oil, and propane all have the same utility rate. Those don't vary, or they do for a location, but not, there's not multiple for a single building, to say that. So for savings, we have stock utility bill savings of 2 to 3%. Again, this is for the whole stock, including non-applicable buildings. But this equates to about $4 billion annually, which would be attributed to that roughly 36 or 34% of buildings applicable to the measure. And then, as we would expect, the standard performance shows lower cost savings compared to the advanced performance. It does still largely show savings, at least at the national level. But I do want to call out that results for these heat pump measures, they vary considerably by climate. I'll probably call this out 10 more times going over the next few measures, and we have some visualizations to help illustrate this later. Okay, so now we are looking at the same measure, standard performance heat pump rooftop unit, but we are looking at a higher lockout temperature. And the reason for this, I said before that the base assumption for the other measure was 0 degrees for the lockout temperature, and now we're doing 32 degrees. So products can vary, and you can even change the setting on the RTU, and we've gotten a lot of feedback that some people have seen heat pumps that do use a higher lockout temperature, and that can have a lot of implications for the performance of the unit. And so that's what we're trying to illustrate here. So in the data set, you will find the standard performance heat pump rooftop unit with a 0 degree lockout and a 32 degree lockout. But we also did a sensitivity analysis with other lockout temperatures down below here, ranging from 0, 5, 10, 17, and 32. And hopefully this helps visualize what the lockout temperature does. The red is backup electric heating, and the blue is heat pump heating. And as the lockout temperature increases or moves to the right, we can see that we're doing more backup heating and less heat pump heating. This is less ideal because the heat pump is going to be much more efficient usually than the electric resistance backup heat. And we can see the implications of that on the COP. So this is comparing the same measure, but with a 0 degree lockout on the left and a 32 degree lockout on the right. And we are looking at the median of the annual average total heating COP for the state. And the COP I'm representing here includes the impact of supplemental heat, crankcase heat, and reverse cycle defrost, but not the supply fan. So the more supplemental heat we use, which has a COP of 1, the more it's going to bring this COP down. And this is pretty apparent here. To the left, we can see the COP dropping below 1 a little bit in some of the coldest regions. I think 1.7 is our lowest. And to the right, we're well below 1 for much of the country because we are not allowing the heat pump to operate for the colder conditions. So it's mostly electric heating for the periods of the year with the higher heating loads. And this has implications on our utility bills as well. The utility bill savings are reduced when we use the 32 degree lockout, almost at parity with the baseline. And of course, again, the results vary considerably by climate. So maybe in a warm region, this does save on utility bills, but in Minnesota, you're largely going to increase your utility bills. Okay, another standard performance heat pump rooftop unit, and this time we're doing a measure package where we couple it with improved roof insulation. This has been another common request, adding heat pump RTUs with different envelope improvements. So we're really investigating the combined effect of improving the roof insulation with the heat pump RTU retrofit. The roof insulation measure was released in our first data set release, and the targets for it are down below. ranging in climate zone for the R value of the roof. We go from climate zone 1, which is the warmest, to 8, which is the coldest, and our R values range from 21 to 37. So the colder the climate, the higher the R value target. And the applicability is going to follow the heat pump RTU applicability here. We're applying to 34% of the stock for these RTUs, and we're only applying the roof insulation if the heat pump RTU measure was applicable. Okay, so we've already looked at what the savings are for the heat pump RTU measure. So now I'm going to focus just on what additional savings did the roof insulation provide. And just to show a different way of looking at the stock savings, we're now looking at the applicable stock savings. So this no longer includes non-applicable buildings. I like consistency in presentations, but I also want to demonstrate the different ways that you can look at stock savings for a measure. So again, this plot does not show the non-applicable buildings. So when we look at how much the roof insulation helped compared to just the heat pump RTU alone, at the stock level, we see 1% additional site energy savings for heating, gas, and electricity, and 5% for cooling. But I do want to caution looking too much into the percent savings for the stock for commercial buildings, because your ability to save a percentage of your energy bill in a commercial building is going to be very dependent on your roof to floor ratio. So if you're talking about a 35-story hotel and replacing the roof, it's really only the top floor that has the opportunity there to reduce its loads. But if you look at a grocery store, which is a big, wide, flat building with a massive roof, those buildings will offer a higher percent savings for roof insulation. And we can see here the impact on utility bills is fairly small at the national level, again, for reasons I just talked about, but we do see about $1 billion of additional annual stock utility bill savings when adding the roof insulation. But if this is of interest to you, I encourage you to review the data set and see where the roof insulation is making the most impact. Okay, so the name here is admittedly kind of a mouthful, but we're aligning with the name of a separate project, the Commercial Building Heat Pump Technology Challenge, which has provided and is continuing to develop a specification to increase heat pump RTU readiness in colder climates. So yes, this is another heat pump RTU measure, but this time the modeling is intended to align with this performance specification. I have both the challenge website and this spec linked above here. The concept for our measure study is the same as the others. We're replacing electric and gas RTUs, but now the RTUs are meeting the challenge specification. So I'm not going to be able to do this all justice here, but a few key assumptions. We now get 100% heating capacity at 5 and 70% heating capacity at -10 compared to the rated cooling capacity. Usually RTUs, when you talk about the tonnage, is rated based on cooling capacity. Compare that to the standard performance, where I think I said around 40% capacity at 0 degrees. So this is a very large improvement in the amount of heating capacity we'll have at lower temperatures, and therefore will reduce the amount of less efficient backup heat. We also have COPs of 1.3 at -10 and at least 1.7 at 5, and our compressor lockout moves down to -10. So we already looked at the impact of the compressor lockout temperature, but now we're moving it in the other direction to further increase the amount of heat pump heating that we can do. And like the other measures, we're sizing to design cooling load and using electric supplemental heat for any remaining loads. I do want to call out that the specification allows manufacturers to develop units with dual fuel heating. We are currently just doing electric heating for this study, but we may study the impact of the dual fuel in future work. But I don't want to give the impression that the specification requires electric backup heating. And as I mentioned, additional details are available at the links above if you're interested in the challenge or the specification. And these performance curves that we've developed, which are outlined in our document, I want to call out that they are one pathway to meeting the specification, and there are many pathways that one could take to do this. So again, we're going to be looking at just the difference between the heat pump RTU challenge units and the standard performance units, rather than looking all the way back to the baseline. Nationally, we see an additional 14% electric heating. This is again for the applicable building stock only. And this is largely due to improved capacity and efficiency at this lower temperatures, as well as that lower lockout temperature, which just allows us to run the heat pump longer. We do also have fan and cooling savings, and those are due to expected efficiency and staging improvements with the challenge units versus the standard performance units of today. So for utility bills, these challenge RTUs against the baseline building stock save about $5 to $6 billion annually in utility bill savings, varying a little bit based on which electricity rate that you're looking at. And this is an additional $3 billion of savings when we compare to the standard performance heat pump RTU scenario. And I am calling out at the bottom that not all buildings show energy bill savings. So we're showing the national average here, but there is a distribution of outcomes for utility bill savings, and some will go negative, indicating an increase in bills. That's going to be more common in the coldest climates, but the challenge units are meant to reduce that and actually lead to bill savings as much as possible. Okay, so now we're again comparing COPs. We have the standard performance heat pump RTU on the left. This is the same plot that we went over a few slides ago. And then we have the heat pump challenge heat pump RTU on the right. And these are these total COPs that include our supplemental heating. So it's pretty apparent that in the colder regions for the standard performance, we dip below 1 for our COP, but the challenge unit, the lowest we see, at least in terms of this median of the averages, is about 2.3. So this is helping us a lot in these coldest climates, and across the country, most of the COPs, or maybe all of them, are a little bit higher, but the intent is to really help the COPs in those colder climates that are dipping below 1 for the standard units of today. Okay, so now we're going to look at a package of measures that we run together. So this is combining our standard performance heat pump RTU, as well as what we're calling an air source heat pump boiler. This is really just a water to air heat pump for a boiler retrofit, and LED lighting. The two heat pump measures are mutually exclusive. They never appear in the same buildings. And the LED lighting, or actually the air source heat pump boiler and LED lighting are both from our first cycle. We do have documentation on those if you're interested in learning more about them. The LED lighting measure is simply replacing non-LED lighting with LEDs. That is another one of our distributions in ComStock. We have different lighting types to assign to different buildings. And so any building that doesn't currently have LEDs is going to be replaced with LED lighting. Package 3 is applicable to about 90% of the stock floor area for at least one measure, but the applicability varies based on the measure. So we outline or try to illustrate that on the right here, the different combinations of applicability. So for example, at the bottom in blue, about 28% of the stock only received the LED lighting, about 26% received the LED lighting plus the heat pump RTU, and so on. Okay, so we also have this package 2. This one we're calling package 3 in the data set. Package 2 we did last cycle, and it's the same thing except we're using that advanced performance heat pump. So if we compare to the baseline, package 3 saves 91% of the total stock heating gas. So we are largely removing and fuel switching gas heating with electricity here. The remaining 9% are just other system types that were not applicable to either of these heat pump measures. We see an increase in heating electricity, again, from fuel switching of 198%, and we have 36% stock lighting savings. This is from the LED measure, of course, and the cooling and fan savings are both largely due to the heat pump RTU. When we compare to package 2, which has the advanced performance heat pump, we do see reduced savings for electricity, heating, fans, and cooling. Still savings compared to the baseline, but just compared to the higher efficiency version of this package, they do reduce a little bit as shown on the right. And these are all due to the difference in the heat pump RTU measure. Okay, demand flexibility measures. So in the past dataset release, we released 2 demand flexibility measures. In the table below, it's the 2 thermostat control ones, load shed and load shift. We are now adding another measure for lighting control and a package of measures. All of our measures for demand flexibility currently use daily demand flexibility events, and each event is 4 hours. And they're applicable to offices, schools, and warehouses, which is about 68% of the stock floor area. But we have these objective functions which determine the timing of the demand flexibility events, which is a very important feature. So I wanted to show all of these in this table just to show that we are starting to do some mixing and matching of these. So if we look at the objective function column, we have building peak load reductions, and we also have emissions reductions. All 4 measures, have the building peak load reduction now. And the emissions reduction we have added for the lighting control measure only. It's the last 2 measures in here that are new to this data set and what I'll be going over today in terms of results. But I just wanted to outline all of this of how these objective functions can be paired with different measures and the concepts of those measures. So now we're first going to look at lighting controls for load shedding. As I showed in the last table, this does a 30% lighting shed during the demand period. The left helps to illustrate this on a single building's load profile where we see the 4-hour demand events. The dotted orange line is the baseline's load for this sample week, and the blue is the lighting load shed load with the measure applied. And we can see during the demand event where we shed load. To the right, we're looking at distributions at the stock level of peak load savings. This is the maximum daily peak reduction for each month. And if we look between the 25th and 75th percentiles, which if you're not familiar with the box and whisker plots is the bottom edge and the top edge of the rectangles, we see about 2 to 7% of the stock daily peak reduction. We can also see that the whisker extends below 0 in some cases or all cases here. That indicates that some portion, a small portion, but some portion of the buildings are actually seeing an increase in their daily peak. And this is one of the challenges with demand flexibility. This can happen sometimes. We try to reduce it as much as possible, and that's a discussion for future work as well, but this does occur sometimes in the data set. In the case of lighting controls, the reason this is happening is because in electric heated buildings, the reduced lighting can increase the electric heating load, which can cause a bigger spike than reducing the lighting caused. Again, most of the buildings are seeing savings, but there are some that are not. Okay, now we are looking at lighting controls again, but now this time we have the emissions reduction factor. So we're illustrating this to the left. This is the same period, but now this demand period has shifted to the right side of the peaks. So we're no longer coinciding with the building peak, but that's no longer the objective. We see our load reductions occurring when the peak emissions factor is the highest. In the lower plot, that is the green line, and we can see where that peaks out. That is where we are targeting our demand events now. And to the right, we're looking at our distribution of savings again. This time it's for emissions factors, and we see 1 to 3% for that 25th to 75th percentile. And again, we do see some cases where emissions are increased for the same reasons as on the last slide. In our last measure slide, we have our package, which combines the thermostat and lighting control for load shedding. So this is the building level daily peak reduction. And to the right, we can see the impact of this on these distributions of our maximum daily peak reductions for each month, ranging between 3 and 12% stock daily peak reduction, also with even greater negatives in some cases. And this is due to adding rebound effect with the thermostat setback measure. We do offer a 2-hour or implement a 2-hour rebound control period to try to mitigate this. But again, this is a challenge with demand flexibility that guaranteeing you will never actually increase your peak after the event is hard to do in a field of continued research. Okay, so switching gears a little bit. How am I doing on time? Okay, so accessing the data set. So there are 5 main ways to look at the data set. We first have our metadata files, which are all annual. So energy results, building characteristics, all aggregated to the annual level. These are in CSV and Parquet file formats, and they're available at the Open Energy Data Initiative for free or ODI. The next 2 columns talk about time series data, or what we're calling load profiles here. We can get the individual load profiles for any building. Again, CSV and Parquet files, and these are in 15-minute intervals. And they show energy consumption and savings. And we also have pre-aggregated the load profiles, hopefully in a way that's beneficial to you all by climate zone, ISO and RTU region, and state. Those are also available at ODI. Then we have our online data viewer. This is a dashboard that allows for CSV exports of various time series and annual data. What I most like the data viewer for is if I want to get a custom aggregation of load profiles. So let's say, for example, I want the load profile of all the buildings in Boston that are offices. You could go to the data viewer, apply those filters, and export the load profile in a CSV format. And then we have our full database available in an Amazon S3 bucket. I'm leaving this here just for reference. This is our field naming conventions. We also have a data dictionary explaining different fields. So if you're looking at our files and you're wondering, what does weight mean? Go to the data dictionary, and there should be a definition for what the column means and the units and all of that kind of stuff. This shows the data structure for the Open Energy Data Initiative, or ODI, as I've called it. So this is just what you will see if you go to that link. The full data set is not yet up yet, but this is a large majority of the links and the data. So first, we have our full resolution metadata by census tract with annual results and characteristics. And then we have our metadata aggregates with various higher geospatial resolution. So this is a change from before that I'm going to go over, I think, on the next slide. So more to come on that. We have our time series data. We have our dictionary of upgrade IDs, and so on. Okay, so back to the new sampling. Again, the new sampling offers a much higher resolution down to the census tract level. Because of this, though, the data files become enormously larger. So we've come up with a scheme to try to handle that. We're offering the annual data in a couple of options. The first option is the full resolution. So this is, again, at the census tract geographic level in our highest resolution. We have broken this up by state and county to help manage file size. So to the right, you can see the folder structure. You would go under metadata and annual results, and you will get a folder for state and county. And we break these up, again, because if we had them in one file, it would be way too massive. You will then see folders for basic and full. The basic files are smaller and they have fewer attributes, so they're easier to manage. The full ones have more attributes, but they're larger. The data dictionary that I mentioned before does call out which fields are available in the basic and full files. So if you're deciding which one to use, you always want to go with the smaller one if you can get away with it, but look at the data dictionary to figure out which one is more appropriate for you. And then we offer CSV and Parquet files. CSVs are larger, but you can read them in Excel. Parquet files are more compact, but they require programming to read. Our recommendation is to only use the full resolution data for sub-county level analyses. So if you're doing analyses for a tract or a city or a part of a city, this could be the path that you want to take. But if you're doing a national study and all you need is averages for a state, we have better options that are less computationally expensive and just require less storage. So we now have our second pathway or option, our annual lower resolution aggregates. So we offer 4 different aggregation levels: national, by state and county, and by state and PUMA. So these are going to be lower resolution, but a much more manageable file size. So the national is going to have state as the highest geospatial resolution, and it's one file for the whole country. The state file is the same as the national, but it's divided up by state. So it's going to be smaller files, and if you only need to look at Texas or California, just grab the state file and you won't have to deal with the larger file size of the national. We also do by state and county, where county is the highest resolution, and by state and PUMA, where PUMA is the highest resolution. This is an example of what one of our metadata files are. These are those annual results files. It's not shown here, but I did mention earlier that building IDs can now be used multiple times. So each row in here is a building ID, as shown on the left. In the new data set, you can find a building ID happening multiple times across census tracts. You'll never find the same building ID within a census tract, but in a county, for example, you may. And then I just call out a few other columns here, for example, like our county, our building type. We do have a weight for each building in the data set. If you see columns that do not have weight in the name, assume it's all unweighted, like I'm demonstrating here. If you see weighted in the name, though, assume that the weighting factor has already been applied. And this is an example of our time series files. So this example is for one building. I did mention before, we also have aggregates by region, but what I'm showing here is just one building for ID 5324. This building ID will correspond to the annual metadata files. So if you want to know what this building is, what are the attributes, what's the annual data, look up 5324 in those annual files. We also have our timestamp. You'll see the first timestamp is 15. Our timestamps are time period ending. So the first time step is 0 to 15. The second is 15 to 30. And then we have all of our consumption values over to the right, which are all in kilowatt hours. This just illustrates what the data viewer looks like that I mentioned earlier. You can look up different geographic regions. By state is what I'm showing here. You can select a certain measure scenario. To the bottom left, I show bar charts that you can go to for annual data and characteristics. And in the bottom middle, we have the time series data. I also mentioned before that my favorite use of the data viewer is getting custom time series aggregation. So if we clicked on Explore Time Series, it would bring you to a page that looks like this, where we can add custom filters in the bottom left, where I call out in the orange box. And then once we get the aggregation that we want, we can export that data to a CSV in the top right. Okay, so that concludes the majority of our presentation here. A few reminders: only use higher resolution annual files from ODI when needed. Always use the lowest resolution you can, just so that your file sizes aren't any bigger than they need to be. With the higher resolution data, weather files will not be as locally specific. We're not doing anything as egregious as using a model from Texas with a weather file in Texas for like Minnesota or something like that. But we will have instances where like a model in Denver that was simulated with Denver weather might be used in Aurora. And if you're not from this area, they're right next to each other. So just note that. Building IDs may now be used across census tracts with locally specific weights. All timestamps are time period ending and are in Eastern Standard Time. The annual metadata files provide weighting factors for national scaling. And if a column already has weighted in the title, assume that that factor has already been applied to it. This can be very helpful if you're trying to quickly get to a state or national aggregation and you don't want to have to worry about multiplying columns together. But just note that difference in the columns when you're looking at them. Although less of an issue, still check your sample sizes on custom aggregations. Too few samples can increase uncertainty. And any column without dot that doesn't have units are in kilowatt hours. Okay, so next steps. I mentioned that data sets are now being released with ComStock in 3-month increments. So we have more data sets this year. We have February 2025, that's just next month. We are not going to do webinars for all of them. We'll probably do one more webinar at the end of the year, but just be aware that this frequency will be occurring. New data sets will be released. What I have on screen here is the list of measures for our next release. I also encourage you, if we have not modeled measures that you want or need for your workflow or have interest in, and you don't see them in our upcoming list, please email us. That's a great way for us to justify your measure to DOE. They're very responsive to what everybody is asking for. So that concludes the webinar. We're now going to switch over to a Q&A. If there are any outstanding questions, I'll pass it over to Andrew.
Yeah, Chris, there are only two sort of outstanding questions that I think would be useful to answer live. The first one is um, for the ideal air loads measure, does this include the outdoor air, so the heating and cooling energy required to heat and cool the outdoor air?
Yes, it does. So the outdoor air is provided, it's mixed directly with this ideal supply air going into the zone. The outdoor air flow rate is going to be determined by the design outdoor air for that space. Um, and it's going to follow the occupancy schedule of a building as an HVAC system ideally should. So yes, the impact of outdoor air is included.
All right, cool. The other question to answer live is, are there units, so heat pump units, on the market which satisfy the heat pump technology challenge specs already?
Not that I am aware of. There are some units that have come out that have called themselves cold climate heat pumps, but I don't know if those meet the full intent of the specification. So that is actually a different team that handles that challenge specification. So they may know more than me, but I forget if I mentioned this. The intent is that manufacturers will develop units in 2025 and 2026 with units that should be available for purchase in 2027. So hopefully that answers your question enough, but if you still, if you want to know the true answer to that, you can reach out to us and I can put you in contact with that team to see if they have seen anything.
Cool, thanks, Chris. I think that answers that one. Um, Another question was, are there any plans to ever update the baseline year from 2018?
Yes, there are, but I'm not sure when. Andrew, I don't know if you have a more precise answer than that.
No, I know that it will not be in 2025 because the 2025 scope of work for ComStock is already defined and that's not in it. If that's something that's important to you, please reach out to us and send us an email of like why that's particularly important and useful, because that's helpful to us when we go to DOE to help prioritize what we want to work on each year. Um, the last question that we have is, what was the hot water temperature that was generated by the air source heat pump in package 3? Did you test with different hot water temperatures to see the COPs?
If we are talking about what we call the air source heat pump boiler, or
Yeah, I think that's it.
yeah, it's an air to water heat pump. We did not do like, say, a sensitivity analysis for testing different supply water temperatures. There is measure documentation for that measure, which outlines all of the details and inputs that we have for that and where we got those data sources from. But I can say that the supply water temperature, I believe at most was 140 degrees Fahrenheit.
Okay, that is the extent of the questions that we've gotten in the chat thus far that haven't been answered.
Okay.
So if anybody else has any more, put them in now or
And feel free to email us as well at comstock@nrel.gov if you didn't get a chance to ask your question or if something comes up later. Okay, I think with that, we can conclude then. So thank you all for attending, and we look forward to seeing you in the future.